Hello everybody, let's start today's lecture. Yesterday we've seen we will continue today the lecture on simulation, and specifically I will start again from rejection sampling. Rejection sampling is a method to sample from a distribution, which is very important to perform a simulation. And as we've seen yesterday, in order to do rejection sampling for a conditional distribution, this is the theorem to do this. And let us assume that x is a random variable, and the distribution of x is the conditional distribution of another random variable x tilde, given that y tilde, another random variable, belongs in an area A. So in order to sample, to take a sample of this random variable x, we perform this algorithm, which is the rejection sampling. So we draw a sample of x tilde and y tilde. We assume that we know a method to draw a sample from x tilde and y tilde. And then we perform this until y tilde belongs in the area A. So if y tilde belongs in the area A, we return x tilde. Otherwise, we repeat the process and we resample. So we applied this theorem in order to draw a sample from uniformly, to draw a point, to draw around a uniform point in this strange area here, A. We don't know a method of how to draw a sample in this area A, but we know a method to draw a sample in the rectangle that surrounds this area A. So therefore, in order to sample x uniformly in the area A, we sample first a point x, y in the rectangle that we know how to do it, and if the x, y belongs in the area A, we keep it and we return it. Otherwise, we repeat the process. Okay, so we saw how to do rejection sampling in order to draw a sample from an area A, given that we know how to draw a sample from a box that surrounds the area A. And we also applied this in the unit disk. So now we will see more things. We'll see how to draw samples using rejection sampling from general distribution. And we'll start from a question for you to get some intuition. So sample x uniformly uniformly between -10 and 10. Compute q, which is equal to f of x. F of x is given here. And with probability q, return x. Otherwise, with probability 1 minus q, resample. Sample again. So what do you think is with this algorithm? What do we sample? What kind of sample we obtain? So the correct answer is A. So we sample. We'll see here the solution. So we sample x with probability that is proportional to f of x, but this is just an intuition, so we will see later why this is correct. And the probability, so we obtain a sample of the random variable that has a probability distribution function proportional to f of x. Now the normalization constant k will be determined such that the total probability is equal to 1. So 1 over k is equal to this integral, which just note that this integral might be hard to compute. So sometimes we don't want to compute this integral. Now we'll see the theorem that for rejection sampling for a distribution with density. So now we want to sample y, to take a sample of the random variable y, which has a distribution fy here, equal to k multiplied by fyn. So in this case, we probably don't know k, or it's hard to compute, but we know fyn. Okay, we know this part of the distribution. Then we want to obtain a sample of this random variable y. Then we also know a method on how to draw a sample from another random variable x. Now for this random variable x, we also know the distribution of course, f of x, and we know that there exists a constant c such that this quantity here, so fyn, the known part of the distribution of y over the distribution of the probability density function of x, fx, is less or equal than c. So this quantity is bounded, and we know a bound c. And we will use this in order to obtain a sample from the random variable y. Okay? Now, a sample of y is obtained using this rejection sampling algorithm. First, we draw a sample of x and u, where u follows the uniform distribution between 0 and c. X, we said that we already know a method on how to sample. We assume this is in our assumptions, that we know how to draw a sample of x. We obtain also a u, which follows the uniform distribution between 0 and c, where c is here, the constant that bounds this quantity. And then, if u is less or equal than this quantity here, fyn over fx, evaluated at x, where x is the sample we obtained above. If this is true, then we return x, and this is our sample. Okay? Otherwise, we repeat the process. Okay? And the expected number of iterations of this algorithm is c, which is this constant, over k, which is the normalization constant, and we may not be able to compute the exact expected number of iterations because we may not know the normalization constant k. Okay? So any questions on this? We will see how to apply this next. Okay. So let's see how to, I want to mention here also that in this case we don't require fyn to be bounded, but we require the fyn over f of x to be bounded. Okay, we will see next a theorem where we require fyn to be bounded. Okay, let's apply this to this distribution, to this PDF, this one PDF, and we want to draw a sample of the random variable y that has this PDF here, fy equal to k multiplied by this quantity. Okay. So first, we don't know k, but we know this part of the distribution of y. So we set fyn equal to this part of the distribution of y. Okay. Then we know that y has a finite support between minus a and a. Okay. And then we choose x. So for x, we need to know a method to take a sample of x. So now we choose x. Okay. So because y has a finite support between minus a and a, we choose x just uniformly distributed between minus a and a. So the probability density function of x will be f of x equal to 1 over 2a. Okay? For x being between minus a and a, otherwise it's 0. Okay, then we know f of x, we know fyn, and we take this quantity, fyn over f of x. And this quantity here is, of course, for x being between minus a and a. And this quantity here is less or equal than 2a, because this quantity here is less or equal than 1. This is 1 over 2a, and this is less or equal than 2a. Okay? So this is our c in the theorem. This is the bound. So this is our c. So let's see how the algorithm now works. We draw a sample of x from the uniform distribution between minus a and a. We saw yesterday how to do this using the random number generator and just scaling the result. Then we draw a sample of the uniform distribution between 0 and 2a in the same way. So between 0 and c, it was in the theorem. So here is 0 and 2a. And then if u is less or equal than this quantity here evaluated at x, at this sample, so fyn of x over 1 over 2a, then we return x. Otherwise, we repeat the process. Okay? So this is just an application of the theorem. So any questions here? No. Now, we can do a simplification in this algorithm, because we see here that we draw u uniformly between 0 and 2a. However, 1 over 2a is also here. So we can just replace, this 2a will go here, it will be u over 2a if we just change parts. And then we can just replace u by v, which will be equal to u over 2a. And then we just need to draw x from the uniform distribution between minus a and v from the uniform distribution between 0 and 1. And if v is less or equal than fyn of x, then we return x, otherwise we go to step 1. Okay? We repeat the process. So here we removed this part because we changed variables. And since u is between 0, uniform takes values between 0 and 2a, v will take values between 0 and 1. So we sampled from the uniform distribution between 0 and 1. Now, okay? So when x follows the uniform distribution in an interval, then we can do the simplification, and instead of drawing between 0 and c, we can draw between 0 and actually the bound of fyn. We will see it in a theorem later. Here is 1, the bound of fyn. And then check if this sample is less or equal than fyn of x. Okay. Let's move on. Now let's see a graphical interpretation of this. So we obtain v from the uniform distribution between 0 and 1, and this is the known part of the distribution of y. And what we do is that we may not know normalization constants, so we know from the assumptions of the theorem the distribution of y up to normalization constant. So here we put v in this axis, so it will be uniform between 0 and 1. So let us assume that is here, the v we obtain, the sample of v. And then we also take a sample of x between minus a and a. Here we have minus 10 and 10 instead of a. And let us assume that the sample of x we obtain is here. Okay. Then we compute, if you see here, we compute fyn of x. This fyn of x will be this value here, up there. Okay? And we see that v is less than fyn of x. So this point we keep it, and you see that it is in the below this PDF of y. Okay. Now let us assume that v was here, that we obtain. We obtain v uniform from 0 and 1, between 0 and 1, and we obtain v equal to 0.6, and this value here. Okay. And we obtain x uniform between minus 10 and 10, and we had this value here, 4.3. Then fyn evaluated at x will be here, and v is here. So if you see, now v is higher than fyn of x. Therefore, this point we reject it. And if you see, it's out, it's above the PDF. Okay? And we reject it. So this is how rejection sampling works. And there, in this graph, we see many points that 2,000 samples that are obtained by rejection sampling from this distribution, and we see that we approximate this distribution. Okay. Let's move on. So this is a rejection sampling when y has a finite support, as before. So we assume that we want to sample y that takes values in a bounded interval between a and b, okay, and has a density function fy equal to k multiplied by fyn, where we know fyn is known, and or we can easily compute it, but the k we can probably we are not able to compute because it's a normalization constant, and the integral might be hard to compute. Therefore, it's unknown, and we assume now that we know an upper bound of fyn, which is m. Okay? Therefore, we choose x always uniformly distributed in over a comma b. So from the uniform distribution between a and b, and then we choose u from the uniform distribution between 0 and m. Okay, where m is the bound on fyn. Then we we return x, and this is our sample. If u is less or equal than fyn evaluated at x, where x is a sample, Otherwise, we repeat the process, we return. So this is very similar to the simplification we did before, because before we had this probability density function, Fy, where k is hard to compute, but we know a bound of Fyn, which is this one. Okay, we know a bound of this one, which is equal to 1. So in the previous example, m here was equal to 1. Okay? And yes, and so this theorem is very useful when we have y that has a finite support. It's between, it takes values in a bounded interval. And when k is hard to compute, but we can easily found the bound m on Fyn. Okay, like this case. Okay. So, any questions up to now? Okay, let's see a question for you then. So the correct answer is F, and this is why A, the distribution, the PDF A is proportional to the distance from the line x plus y equal to 1. Okay, so this is the line x plus y equal to 1, and it takes higher values. So we have more samples away from this line, and the correct is C, so C here. Then B is constant, so it's uniform, and it's there where we see uniform distribution. So it's the second graph. And C is proportional to the distance from the center of the reticle. So we will have more samples away from the center of the reticle. So C is A, is the first graph. So first C, then B, and then A, sorry, before I got confused. Okay. So this is the solution. Describes the same thing. And another question for you. Let's see the answer. So the first algorithm says that we sample x and y uniformly in between 0 and 1. And then if we obtain u that is uniformly distributed between 1 and 1 over square root of 2. And if u is less than c, evaluated at the samples of x and y, we return x and y, otherwise we repeat the process. The second algorithm is the same, and the difference is that it samples u uniformly between 0 and 1. So based on the theorem that we've seen before, and the simplification, what we need here is a bound on C, a bound M on C. And this algorithm uses the bound 1 over square root of 2, and this algorithm uses the bound 1. Okay? Both are correct bounds for C. So C is less or equal than 1, and it's also less or equal than 1 over square root of 2 if you compute it. So both algorithms are correct in order to take a sample of x and y with PDF proportional to C. Sorry. But how do we compare the two algorithms now? Both are correct. In order to compare them, we check the number of iterations that rejection sampling takes in order to give us a sample, as we did yesterday for the unit disk. Okay? So based on the theorem, the number of iterations is C over K. Okay? So C we know, K we don't know, but it doesn't matter. So C in the first algorithm is equal to 1 over square root of 2. So the number of iterations the algorithm A takes is 1 over square root of 2 multiplied by K. Okay? And K is the normalization constant. It is given by this, and it's by this integral, and it's unknown. It's hard to compute, or we don't want to compute it. The average number of iterations of the algorithm B is 1 over K, because C is 1 and over K. So it's 1 over K. So algorithm A takes less iterations, so it's more efficient. It is expected that it will give us a sample in a fewer number of iterations. Okay?
For the option A, it should be uniform 0 and 1 over 2.
Yes, it's a typo. Correct. It's also here a typo, yes. Thank you. Okay, let's see another example now. We want to sample a random, we apply again rejection sampling here. So we want to sample a random vector, x1, x2, that takes values in the unit square. And the distribution of the vector has a density proportional to x1 minus x2 absolute value. Okay? So it's further away from the line x1 equal to x2. Then we take now f of x, the uniform distribution in the unit square. Okay? So we need to choose an x variable that we know how to draw a sample. So we choose the uniform distribution in the unit square for this as a distribution of this random variable, which is now a vector actually. And then Fyn is equal to x1 minus x2. Okay? So this is the part of a distribution of y that we know. So y will be, Fyn will be this one. The density of y is proportional to x1 minus x2. And the density of x, according to the theorem, is uniform in the unit square. Okay? Now x and y are vectors. Then we draw x, so we draw x1, x2 in the unit square. And then we draw also u from the uniform distribution between 0 and 1, because this Fyn is upper bounded by u1. Okay? So this is not needed here, because Fyn is upper bounded by u1, because these take values between 0 and 1. So this is upper bounded by u1. Because this also Fyn is 1, this distribution. So this is bounded. We just need a bound of Fyn, which is equal to 1 here. Okay? So we draw u from the uniform distribution between 0 and 1, which is the bound of Fyn. And then we draw x, x1 and x2, because x is a vector. And then we check if u is less or equal than Fyn evaluated at the samples x1 and x2. Okay? If this is true, then we return x1 and x2 as our samples. Otherwise, we repeat the process. So we saw here how to apply also rejection sampling for a random vector. And then these are the samples that we obtained by rejection sampling. And we see that this is the line x1 equal to x2, and the samples are more as further away from the line we are. Okay? So any questions up to here? Because I will move on to a different topic. No? Okay. So we've seen the methods to draw samples, but probably there are optimized methods for some distributions, and it's good to use them if they are implemented in the tool that you are using. It's good to use them because they reduce the computational time. Okay. For example, for a normal distribution, the CDF inversion method that we saw yesterday is hard to compute, is hard to apply, because we need to compute the F inverse, as you remember yesterday, and there is no closed form for that. So it's hard to apply the CDF inversion. We can apply rejection sampling for the normal distribution. It's possible. But there are more efficient methods. For example, with a change of variables in the normal distribution, we can draw a sample from the normal distribution using the Rayleigh distribution, which the F in there can be inverted, and the uniform distribution. Therefore, there are more efficient methods, and it's good to use them. So there are efficient methods for drawing two independent normal random variables, and also for n independent n-dimensional normal distributions of Gaussian vectors. Okay. So let's see now some samples of a Gaussian or of a random Gaussian vector x, y that has a 0 mean. So the mean of x and the mean of y are 0, and this is the covariance matrix. So the variance of each one of them is 1, and the covariance is 0. So they are independent, x and y. And the Gaussian vector looks like this. Okay. So this is x, this is y, and it looks like this. If we plot the points that are sampled using normalized, an optimized method probably. And then we have another Gaussian vector that has 0 mean, and the covariance matrix is this one, which means that the covariance now of x and y is 0.5, and means that x and y are not independent. And here we see that we see a trend here. It's not like the other one. So here we see that they're not independent. Okay. So a question for you. It's simple. What's the distribution of y if we know that x and y is a Gaussian vector with 0 mean and covariance matrix this one? Most of you replied A, which is the correct one. And let's see why. So the marginal distribution of a Gaussian random vector is also Gaussian, so y will have a normal distribution. And the mean of the Gaussian vector is 0, 0, so the mean of y will be also 0. And the variance is obtained by the covariance matrix. So this is the variance of x, this is the variance of y, so is 1. This is the covariance of x, y. Okay? So the answer is A. Any questions? No. So we'll move now to the Monte Carlo simulation. We'll see how to use Monte Carlo to compute the quantities that are integrals or probabilities and that can be expressed as expected values. Okay. For example, a probability that x belongs in the area A can be expressed as the expected value of the indicator function that x belongs to the area A. Okay, so a probability can be expressed also as an expected value. So we see, we assume the idea of Monte Carlo is that we want to compute beta here, which is an integral over probability. And the first thing we do is that we express it as an expected value. So beta equals to expected value of phi of x. And what we do is that we simulate as many independent samples of x as we want. So we learned the method of sampling from a distribution. So we can apply one of the methods we've learned to take different samples of x from the distribution of x. And then we estimate the expectation here. We estimate it by the mean. Okay. So we generate R replicates XR, where R takes values between 1 and R. These are the replicates of X, the samples of X we generate, we simulate. And then in order to, the estimate of beta is equal to this mean. So we take the mean of, we evaluate phi at x of r for each x of r we have obtained, and then we obtain the mean, we take the mean of all these samples, and that is our beta estimate. Okay, so it's simple. However, this is random, so we have to compute a confidence interval for the mean. Okay, so we need to do this also at the end. So we need to know how to generate samples of the random variable x using one of the methods we've learned before based on the distribution of x. Then we take different samples of x, we estimate the expected value with the mean of all these samples, and then because this is random, we need to compute a confidence interval for the mean. Okay? So this is a simple idea, and let's see a question for you, how to compute this. So what we want to do here is we want to compute this integral that is the average distance between 2 points that are uniformly distributed in a unit square. Okay, so this shows the distance. The uniform distribution is 1, the PDF, in the unit square. So which one is the correct implementation of Monte Carlo? So let's see A first. A draws R points in the unit square, MR and NR. So each time it draws a pair of points, okay, and then takes the distance of these points of each sample, and then computes the mean of these distances. and then takes also the standard deviation of all these distances, and then computes a confidence interval. But this confidence interval here is not the correct formula of the confidence interval. It's actually the prediction interval. So basically what the sampling, the computation, the way to compute the estimate of beta is correct, but then it uses a wrong confidence interval. Okay? Now the second algorithm, B, does the same thing as A up to here. So computes the same estimate of beta and the same estimate of the standard deviation, but simply doesn't use the functions of the tool, let's say the functions mean and standard deviation, but does it like manually somehow. Okay, so sums up the distances for each sample, and then takes the mean of these, and also computes the standard deviation. But it uses the correct formula for the confidence interval of the mean. So that is why the answer is B, and that is the correct algorithm, and this is not correct, because it's important afterwards, after Monte Carlo, to compute also the confidence interval for the mean. Okay? So let's see now some more things about Monte Carlo. As we said, we need to obtain a number of replicates of the random variable, and then estimate the expected value by the mean. But how many replicates should we take? In general, we should take a large number of replicates. Okay. So let's see now different estimates we computed for beta, for this integral that we discussed before, for different numbers of replicates. So initially we had one, so we know here that the true value of this is equal to 0.5214. Okay, we know this is the true value. And then for different number of replicates, we obtain these estimates and these confidence intervals for the mean. Okay, so we see that as we increase the number of replicates, the estimate goes closer, but also to the true value. But also the confidence interval becomes smaller. So initially, so the lower bound increases and the upper bound decreases, and at the end is small enough, and it includes also, as we've seen, the true value. Okay. So as we increase the number of replicates, we become more certain about our estimate. We have less uncertainty about our estimate. Okay. So it's good to use, if we can, computationally, it's good to obtain a large number of samples to use when we're using Monte Carlo. Okay. And finally, a final question for you. Actually, we cannot do differently. We should use the confidence interval for the mean, because as we said in Monte Carlo, we estimate the estimate of the expected value is given by the mean on the replicates that we take. Okay, so we cannot do differently. We assume we don't have heavy tail distribution, but we want that R is large. Okay, so we should use the confidence interval for the mean, but we should have a large number of replicates. And this is what we do when we have Monte Carlo. We should use a large number of replicates to be also more certain about our estimate. Okay. So this is it for today. So let's sum up what we've seen in these two lectures. So when we perform simulation, in order to perform correctly simulation, we should first, if it's non-terminating one, we should first account for the transient state. So we should measure our output when the simulation is in a stationary regime. Okay, so this is by observation of the output of the simulation over time. Then, because the output of a simulation is random, we need to measure the accuracy, so we need to use confidence intervals. And we need to know how to sample from a distribution, and this is done by rejection sampling or CDF inversion. So between the two, if you can apply CDF inversion easily, it's better to apply CDF inversion because in one iteration you obtain a sample just with one computation. Whereas with rejection sampling, you might do many iterations in order to obtain a sample for your random variable, and it's computationally more complex. But however, CDF inversion cannot be applied in any case. Sometimes there's no closed form formula for the F inverse. And also for CDF, for rejection sampling, you have, if you correctly choose the distribution or the bounding box, or the distribution from where you sample, the bounds, sorry, that you use for sampling, then you can have smaller number of iterations and become more efficient. Okay? And then sampling and confidence intervals will be used also for Monte Carlo, that is efficient in order to compute quantities that can be expressed as expected values, like integrals and probabilities, okay, by simulation. So any questions? Because that's it.